Today's lecture will be on support vector machines, one of the most powerful and versatile machine learning algorithms in our toolkit. In this session, we will delve into world of SVMs, exploring their theoretical foundations and hands-on implementation using Python. In our first snippet of code, we will try to generate a data. So in these lines of code, we are generating a dataset with 300 data points and two features using NumPy's random functions. This line of code over here sets the random seed to 10, ensuring that you will get the same random numbers every time you run this code. Setting a seed is helpful for reproducibility. In our next line of code, we are trying to generate random data for the dataset X. It creates a 2D NumPy array with 300 rows and 2 columns, resulting in 300 data points with two features each. The data points are drawn from a standard normal distribution, mean equals to 0 and standard deviation equals to 1. And in this line of code, we are generating labels for the dataset Y. We are creating a NumPy array where the first 150 elements are labeled as 1 and the next 150 elements are labeled as 0. This setup results in a binary classification problem with two classes where 1 and 0 represents the two classes. The dataset that we will get from this code can be used for various machine learning tasks such as classification or clustering. In our next block of code, we will try to create a scatter plot to visualize a dataset X and labels Y. So this first line of code uses matplotlib's scatter function to create a scatter plot. These two arguments over here specify X and Y coordinates for each data point in the dataset. This single argument over here represents the values of the first feature x1 for all data points, whereas the second argument represents the values of the second feature for all data points. C equals to y determines the colors of the points based on the values in the y array. It means that the points with y equal to 1 will be yellow color and the points with y equals to 0 will be blue color. The coloring is commonly used in binary classification to distinguish between two classes. The X label and Y label, these two lines set labels for the x-axis and y-axis of the plot. In this case, x1 and x2 are used as labels to indicate which features are being posted on each axis. This is how we are getting two different colors using C equals to Y based on the values in the Y array. Such plots allows us to visually inspect the distribution of our data and see how well it can be separated into the two classes based on the features x1 and x2. Let's move on to our next line of code. In this code snippet, we will modify the x values for specific ranges of our dataset to separate the samples further along the first feature x1. This first line of code adds 2.5 to the values of the first feature x1 for the first 100 data points in our dataset. Essentially, it shifts the x1 values of the first 100 samples to the right, which is positive direction, by 2.5 units. This operation effectively moves these data points along the x-axis. In the next line of code, this line subtracts 2.5 from the values of the first feature x1 for the next 50 data points in our dataset from index 100 to 149. This shifts these data points to the left, which is negative direction along the x1 axis by 2.5 units. By applying these shifts to the x1 values of specific data points, we are effectively creating a separation or gap along the x1 axis in our dataset. Thus, after making these shifts, we can visualize the modified dataset to observe how the separation along the x1 axis affects the distribution of the data points. In the next line of code, we are using matplotlib to create scatter plot of the modified dataset. The plot.scatter function is used to plot the data points where these two arguments represent x and y coordinates of each data point respectively. The color of the points is determined by y array where different colors represent the two classes 0 and 1. The plot.xlabel and ylabel functions sets labels for the x-axis and y-axis respectively to indicate which features are being plotted on each axis. And finally, plot.show displays the plot. Running this code will help us to visualize how the data points are distributed in the modified dataset after the shifts along the x1 axis. We should see a separation or gap along the x1 axis, which can have implications for the performance of classification algorithms on this data. Let's move on to our next line of code. In this code, we are splitting our dataset into training and testing sets and then fitting a support vector machine classifier to the training data. This first line of code uses scikit-learn's train test split function to split our dataset x and y into training and testing sets. X train and y train over here represent the training dataset, and x test and y test over here represents testing dataset. The random state parameter is set to 10 to ensure reproducibility. It determines the random shuffling of the data before splitting. This line over here creates an SVM classifier M with an RBF, which is radial basis function kernel, and sets the regularization parameter C to 1 and the kernel parameter gamma to 1. This line of code over here fits the SVM classifier on the training data X train and corresponding labels Y train. The SVM learns the decision boundary based on the training data and parameters we specified. And at last over here, we are trying to print the accuracy score of the trained SVM classifier on the testing dataset X-test and Y-test using the score method. The accuracy score measures the proportion of correctly classified samples in the testing set. Thus, after running this code, we are getting accuracy score of the SVM classifier on our testing dataset. This score provides an indication of how well the SVM model generalizes to unseen data. In our next line of code, we are using plot SVC function to visualize the decision boundaries and support vectors of the trained SVM classifier on the testing data X-test and Y-test. When we run this code, we will get a display of a plot showing the decision boundaries and support vectors on the testing data, allowing us to visualize access the model's performance. In our next line of code, we are retraining the support vector machine classifier with a higher regularization parameter C, which effectively reduces the margin and allows for more flexibility in the decision boundary. This first line of code, as we have seen earlier, is same, but we have larger C value over here in this code. The higher C value allows the SVM to be less strict about misclassifying points in the training set. potentially resulting in a more complex and flexible decision boundary. In the next line of code, we are fitting the SVM classifier on the training data X-train and Y-train. The SVM learns the decision boundary based on the training data and new parameter settings. And at last, this print statement calculates and prints the accuracy score of the trained SVM classifier on the testing data X-test and Y-test using the score method. The accuracy score measures the proportion of correctly classified samples in the testing data. Thus, by running the value of C, as we have increased it, we are allowing the SVM to have a smaller margin and potentially fit the training data more closely, which can lead to better training accuracy. In this next block of code, we are trying to visualize the decision boundaries and support vectors of SVM classifier with increased C value on the testing data X-test and Y-test. This visualization right over here is helping us to assess how the increased flexibility affects the model's behavior and its ability to separate the classes in the testing data. Thus, a more irregular decision boundary seems to be at risk of overfitting the data. We can perform cross-validation using grid search CV in our next line of codes to select the best choice of gamma and cost of an SVM with a radial kernel. In this code, we are performing a grid search to find the best combination of hyperparameters and gamma for SVM classifier with an RBF kernel. In our first line of code, we are defining a parameter grid for a grid search. It specifies list of values for the C parameter and list of values for gamma parameter. In the next line of code over here, we are creating a grid search CV object which is called M from scikit-learn. This object is used to perform a grid search with cross validation to find the best combination of hyperparameters. SVC kernel RBF. This specifies that we want to use an SVM classifier with an RBF kernel. CV equals to 5 specifies 5-fold cross validation, meaning the data is split into 5 subsets. And scoring equals to accuracy specifies that we want to evaluate the models based on accuracy. Param over here is just parameter grid defined earlier. In the next line of code, we are fitting the grid search CV object M on the training data X-train and Y-train. During this process, it performs a grid search with cross validation to find the best combination of C and gamma that maximizes accuracy. Later on, after fitting the grid search, we can access the best combination of hyperparameters using best params attribute of grid search CV object. This line prints the best hyperparameters found during the grid search. Thus, the C and gamma value that we are getting over here, those values are best parameters that are crucial for fine-tuning our model to achieve better performance.